So why graph? We're not just doing it to draw pretty pictures, although some of them are pretty. In order to draw a graph, you need numbers, you need data. And the human mind is not very well adapted to looking at a list of numbers and drawing conclusions from it. It just doesn't work that way. If there are just a few numbers, yeah, maybe. But it's much easier for the human mind to wrap its brain around data if it's presented in visual form. And graphing your data is one way to do that. And what we're interested in this particular exercise is one type of graph. We're staying in 2 dimensions, right? Flat on the board. So you would have the Cartesian system. Do they teach this in math class, or you have to go into algebra to get it? You remember? Did you get any graphing in math? Okay. So your Cartesian system divides your space into 4 quadrants, right? And this is the x-axis, or the abscissa, and this is the y-axis, or the ordinate. And they're marked off in for our purposes, in equal divisions on either side. Right? There are various types. You can get logarithmic scales, you can get exponential scales where the paper is actually set up that way. So when you put your data in, the idea is that when you put your data into one of those special types of paper, it straightens the curve out for you. But we're not going to do that. We're going to look at just arithmetic, equally divided. Everything on this side, x is positive, and everything on this side, x is negative. Numbers. Okay. Everything below the line is negative for the y and positive here. Okay. So that's the general layout. When we plot numbers data on this, we actually need 2 numbers to plot our data points. And that's in a whole lot of chemistry and the sciences in particular. The data will come out as pairs of numbers. So you can have a list over here, and these numbers go in pairs, and the pair of numbers represents a data point. Something happened, and that's the result. You get a number here, a number there, there, like that. So if we had, say, I don't know, a number 5 here, and over here we got a number 5 as a result, then we would go out 5 here, and then up 5 here. 1, 2, 3, 4, 5. So it'd be right here. And that sometimes in math class, particularly, you're required to identify that point as 5, 5. Right. So 5 is the x and 5 is the y. Okay, that's the data point. But in the sciences, it means a little more than that, rather than just plotting the data. If this axis is reserved for an independent variable, right? The independent variable is what the researcher does, and the dependent variable here is what the experiment does in response. So I do this, and the experiment spits out this. So our xy is independent dependent in that form. Okay, so always ask yourself, if the question arises, which is the independent and which is the dependent variable, and say, all right, which one did the researcher change? Which one did the researcher put in? And then the other one spits out of the experiment is the dependent variable. Okay, oh, I forgot to name this. This is the origin. And it's always 0, 0. Okay. So when we plot our data, it can come out in various forms, right? If we have this list, it could come out and actually give us a relationship that looks maybe something like this. And if you connect all those dots together, it'll give you a straight line, okay? Anything inside your actual data, if you say, all right, so I know this one is true, this one is measured, but I want to know what happens if we say, if we're at this point, right, what would the y be? That's called interpolation. And you're pretty safe interpolating because it's bound by actual data points, right? So you're safe, you're much safer in there than you are anywhere else. If you want to know what if I extend the line, right, in either direction, and you say, all right, what if I pick a point here and say, what would the xy be here? This is called extrapolation. You're not as safe in those regions because you've got nothing out here to prove that you're doing right. I mean, for all you know, it could go straight that way, and then all of a sudden it could go like that. You don't know. You're just assuming that it continues straight. Okay. Sometimes your graphing won't be a straight line. It depends on the relationship of the variables. So if I draw a little one down here and say I'm only dealing with reality, right? All my measurements are positive and all my responses are positive. So I only want this quadrant. Well, some graphs, as the x gets bigger, the y gets smaller. So if I have a data point out here that's like that, and maybe like this, okay, that represents a certain x and a y. But if a y gets bigger, then if the x gets bigger, then the y gets smaller. Now I'm over here, and now I'm over here. And as the x gets smaller, the y gets bigger. So you could have a curve like that. Okay, we see that quite often. This relationship where you have a straight line and as x gets bigger, y gets bigger, this is a direct relationship. And actually, it's a positive direct relationship. You can have indirect relationships, inverse, excuse me. This is a direct relationship. This is an inverse relationship. So as x gets bigger, y gets bigger. Here, as x gets bigger, y gets smaller. This is an inverse. But you can also have inverses that are straight lines like that. Okay. So what do we know about that in terms of math? Right? If we represent this straight line with a formula, everybody knows about what? Y equals mx plus b, right? That's your standard straight line formula. This is the slope of the line. So what's b? Remember? It's the y-intercept. That's where the line would cross the y-axis. So this b would reference this point right here. And the slope is what? Rise over run, right? So it's a change in y for every change in x. So if x changes a certain amount, y changes a certain amount. And if the number is big, that means y changes a lot for a little bit of x change, which means the slope would be like that. But if y only changes a little bit for the x in relationship to the x, it would be like that. Okay, but it would still be positive Positive slope goes this way. Negative slope goes that way. Okay, if it's a straight line in an inverse relationship, then the m would be a negative value, right? Because y is decreasing as x is increasing, and that makes it negative. But if you get a curve like that, how do you apply a slope to that line? Right? Because at one point it's like this, and then it's like this, and then it's like that. You don't. There are ways to describe that curve, but we need calculus to do that. So we're just going to say, at any point on this line, if it's a negative, or even if we did positive, doesn't matter. If it's a curve, then what we're saying is at a particular point, the tangent to that, the slope of that line. And if we pick one down here, well, now it's got a different tangent and a different slope. Right? So it's a changing slope for curvilinears. Okay, so now let's get into the practicalities of drawing a graph. And I'm going to erase the whole thing. In fact, I think I need a new marker. I'm about to give up the ghost. All right. So if you've got a set of data and you've got a sheet of this graph paper, let's see, do I have any extras in this one? No, this is the key. It won't have the extras. But you should have several sheets of graph paper on the back side. I hope they're still there. Check. Yeah, good. Okay. How do you know what to do with that graph paper? To give you, see, what you're trying to do is convey information to your reader. Somebody who's reading your report and you're referencing that graph to make a point, to convince them of your position. You're saying, this is what I think the data means. And you're pointing to that graph to say things about it. Well, you want it to be readable. Right? You want to use all the space that's given to you. And you want the reader to be able, if they want to go into that graph and pick out points that may not be your measured points, but might be different points. Right? So you want it to be logical the way you set it up. So in a typical graph paper, you've got, say, in our case, 8.5 by 11. Right? That's more like 8.5 by 14, but forgive me. Or you could turn it sideways. Right? Right? Everybody knows this is portrait. What's this one? Landscape. Orientation. You got to decide which way do you want to orient. Okay, so how do you decide whether you want which way you want to orient? You look at your data. All right. If you're going to do it on this one, and you have, well, I'm not going to draw all the hash marks in there. But if your x-axis is the smaller range of numbers, it probably should go this way. And the bigger range should go this way to give yourself more room. But if the x is a wider range than the y, then you should go on this one. Okay, orientation. Okay, so next, you decide, and this is already given for you because presumably the information was either generated by you or given to you in terms that you can understand as dependent, independent. So once you decide that, then this is going to have the independent variable. This is going to have the dependent variable. Same as over here, independent, dependent. That's just by convention. Okay, so now what do? Well, you definitely want to label your axes, right? Because if you just throw numbers up there and you don't tell them what they mean, you're just wasting your effort. So you need a label down here. So this is something X, and you want your units of measure, right? So let's just make something up. Say this is volume, say milliliters. And this is going to be Y, whatever the Y happens to be. Let's just do it like this. If that's volume, we're going to say it's volume. And this Y is going to be, say, mass. So it's mass. And this is going to be in, say, grams. So you got your units of measure, you got your name for the axis and your units of measure. And then before we go too far, you need to label your graph. I mean, title your graph, I should say that, title. What is the title? What is it trying to say? In my experiment, I measured the relationship between mass when I changed the volume. Okay. Overall, this is your overriding concern. Every graph you ever draw must stand alone. You have to have every bit of information in here that you need to understand what the graph is saying. So you may also have to put footnotes on the graph. You won't have to do any of those for your exercise, but that's just for future reference. The graph needs to stand alone. So now that we've got the title, we've got our labeled axes, now we got to decide how are we going to subdivide our units. Well, if this one's going to be the bigger one, you need to say, what's my range of numbers? How high do they get? And then say, all right, so if I subdivide it, if I look at the hash marks and I say 1, 2, 3, 4, 5, and that's my data's over with, right? That wastes a lot of space. What if you say, instead of just taking one unit, take 2 units for 1? 1, 2, 3, 4, 5. That uses more of your space. Okay, you spread that one out. Do the same thing for this one, right? So then when you draw in your graph, it takes up most of the available space. And then you can see more detail. Okay, so that's the first thing. The second thing is, depending on how your graph paper is marked off, you want to say, how should I mark off my axes so that I can read the information or plot the information? So your graphs are going to be graph paper. Let me get my copy right here so I can be talking about the same thing. Okay, so you'll notice in this graph paper, you've got light lines and heavy lines. Okay. In between the heavy lines, you've got 5 light lines. Okay, so if we were going to go decimal, then it would stand to reason that you would go over 2 actually and get 10 subdivisions. So you could do maybe tenths or hundreds depending on your major. You got major and minor units. And then if you do graphs in a graphing program, they call them tick marks. Okay. So you have major tick marks and minor tick marks. So the major tick marks might be every 2 groups would be a major tick mark, and then you would have tenths of that mark would be your minor tick marks. And you want to match that up so that you still, you can read it easily and you can cover the distance that's available. Sometimes you can't get it exact. But that's why they're divided that way. And then you go in, once you've identified how far you can go, then you take your data and say your X, Y, or your volume, mass. And you say volume this way and then mass this way, and mark your point. Okay, and do that for all your data. It could be a straight line, it could be curved, who knows? That's the beauty of graphing your data. That tells you something about the information that you wouldn't normally see by looking at the numbers. It tells you what type of relationship you have, whether it's linear, whether it curves, and which way it curves. Okay, let's see.
Dr. Bly, do we need to copy what you've written on the board on our paper?
No,
Or does
I'm
that okay.
explaining.
Okay.
Right. When you draw the graphs, you base it on what's in the procedure. And
Okay.
I'll get there in just a second. Yeah, I've got another hour, I think. Let me see. And also, now, and once we draw the curve, we can calculate the straight line. If it's a straight line, you can calculate the straight line because it would be like this, like this. Well, it's off the paper, but like that. And you want to know the slope. So you want rise, like if you're starting from here, rise, change in y, change in x. And then if you find out what is that distance between here and here, and divide it by the distance between here and here. Okay, that would be your slope. Now your slope is usually more accurate if you spread out the numbers far apart, right? If you got a one up here and one way down here, that would be better to use those. And if it looks like a straight line, then you can use this measured point and that measured point to do your delta y and delta x. And that gives you the slope. That gives you m equals some value. Then you want to find out what the intercept is. Well, if you take a straight edge and draw your line and extrapolate, then you can read the b from your graph, right? That's one way to do it. Or what else can you say? You can say y equals mx plus b. And if you know what this one is, you've calculated it already, then you can go to your data set and say, I've got an x value and a y value together at one of these points, plug them in. Now you have an equation and one unknown, solve for it. Okay, that's two ways to do it. You can do it graphically or you can do it mathematically. Okay. Now, the units of measure here are important. When you draw this graph, then the units of measure are given in your data set, right? X is going to be so many, in this case, milliliters, and the Y will be grams, so you put those in. But if you do any transformations, and there's one example of a transformation in here where you take the volume, you've got the, let's see, I think it's pressure and volume. You have values here. That's Boyle's law. But you want to transform data and plot it differently. Well, the method calls for taking this one and doing the inverse of it. Just take this number and divide it into 1. Or on your calculator, hit the x to minus 1 or whatever key is. And write those data points in there. And then plot this number against that number, not this one. Plot these two. Okay? So, if this pressure is in atmospheres, and this pressure is in liters, this volume is in liters, what would the units of measure be for that one? Remember, when you do math on a number, you do it on the units also. So if we take the inverse of this, we take the inverse of the units. Okay? It could be milliliters, it doesn't matter. But if you invert the number, you invert the unit also. So down here, if you did that, then instead of milliliters, it'd be milliliters to the minus 1 power. Okay? I'm trying to make sure that you get a good rate. So I'm pointing out the places where people stumble. Okay, example of that is on page 19 with this pair of, this is pressure times volume, gives you that curvilinear. And then this is the inverse where you do plot pressure against the inverse of volume, gives you a straight line. And then of course, you have to reconfigure your graph for a different set of numbers because they're not these numbers anymore. So you got to go to a different graph and lay it out like this and say, okay, how do those numbers lay on my axis? Because you're using a different set of numbers. You just transformed them. So you can't use these anymore. You can't use that axis anymore. You have to lay out a new one. Okay. Oh, this particular curve right here, where you have pressure times volume equals a constant value. Notice if this is constant, as this one goes up, that one has to go down, and vice versa. Otherwise, that's not constant. So if you plot this information, you get that curve. And in fact, in the math class that any math teacher will tell you, that is a hyperbola, excuse me. English teachers say hyperbole. That's exaggeration for effect. But hyperbola is a curve where the tails of your curve approach the axis but never touch it for infinity. Okay. This exercise also has, I think it has a required and a bonus section. Yeah, the required section goes through number 9, and then starting with number 10 is bonus. So you can do that one, you don't have to do it. But I give you the points that it's worth. And this is an informal report. So you do it in the document and turn that back in. Okay. All right. So let's look at what's required here. You got some really funky curves in here. This one is called a sigmoid curve, right? It looks like an S. This is characteristic in chemistry of a titration curve, where you're adding acid to base and measuring the pH or a number for acidity. And you're plotting how much base is added and the pH. So you get this sigmoid curve. We'll look at that in more detail later. This is called a broken curve. It goes along here, and then all of a sudden you've got to go back up here to get things done. And these are both in the bonus section. So you can leave them if you don't want to do them. It's okay. Required section. Okay. The first page is easy, right? It's just definitions. You just look in the body of the method and answer the questions. So I'm not going to go over those. We talked about those already. This one might be a problem. What 5 items must you consider when selecting the size and range of the scale units for X and Y? Right. What do you need to consider? Well, let's see. One is, what's the maximum range of each axis? Right. What's the maximum range? Also, what does that range tell you about orientation? That's number 2. Do you need to orient it this way or that way? My brain moving slow. A cheat sheet. Orientation, maximum range. Okay, I got those 2. How about the units of measure? Right. The units of measure are going to tell you whether it's, you may change the units of measure if you desired. Right? You could change, as long as they're proportional, right? Instead of milliliters, you might make liters. Or you might want to say cubic centimeters if it references a solid rather than a liquid or a gas. Well, if it's a gas, you probably want to put liters in there, but it depends on your data. So that's 3. Units of measure, orientation, maximum range, whole number divisions. What are your scale units, right? What does each one of these blocks represent? What are your major tick marks? And then how many minor tick marks are between them? So I just gave you all 5 answers. Okay, what does the data point represent? Think about it this way. When you put a point on that graph, where did it come from? Came from an experiment, didn't it? You did something here, and your experiment said that, this and that represents a point, right? So the data point that you put on that graph is an experimental measurement. That's in the body of this thing too. You can look it up. Check me to make sure I'm not pulling your leg. Now, should we expect all of these points to lie on a straight line? If we suspect that it's a straight line, right? Kind of stand back and say, yeah, it looks like it's pretty straight. Should we expect every point to lie on this straight line? Like if we put a straight edge up there, right? Are they all going to lay on that straight line? Probably not. But we try best fit. So what do we mean by best fit? You minimize the deviation from the straight line. Right? You may have to do like this, or you may have to shift it like that, but you want to have a minimum amount of distance between the straight line and each data point on average. That's a best fit. You can do it mathematically, right? The statistical analysis will do that, but we're doing this hands-on graphically. So you set up, and what's the best type of straight edge to use for something like this? One that you can see through, right? Because you might be covering up some of your points when you do that. So a transparent straight edge works best when you're doing a manual best fit. Okay, I already gave you 5 and 6. All right, so when we get to 7. Yeah.
Dr. Bye. So for number 5, the question is, why should we not expect all data points to fall on the straight line? And so we were saying that it's because you can't really predict the way that it.
You're real close.
Like
we can sum it up. We can sum it up in 2 words.
Okay.
Experimental error. Every measurement, and we went through in class, we mentioned this. Every measurement has error.
Okay. Should we say the 2 types of error as well?
It's not called for. No.
Okay.
You're right. In this one, it's not called for. You're talking about whether it's random or what's the other one? I'm sorry. Systematic. Thank you.
Okay.
I claim the privilege of elders. Mine fades occasionally. Okay, so when you get down to 7, I'm going to let you do that one because all you have to do here is pick out which one's the independent and which one's the dependent variable. And all you have to think about is which one did the experimental have control over? Which one did the experimenter change? And then the response is the dependent. Same thing for number 8. 8 parentheses 1. 8 parentheses 2 is where you draw a graph. So you're going to draw a graph with this data up here, temperature, volume. So 8 parentheses 1 tells you which one is the x-axis. So when you answer 1, that tells you which one did you change and what was the response. The response goes on the y-axis. Okay, and then you draw your graph to answer number 2. That's why it's worth 10 points. Because I'm looking for these various things I told you about. I'm looking for title. I'm looking for properly segmented axes and labeled axes, right? Your major, you don't have to label every little tick mark, just the major tick marks, right? If you label the major tick marks, then the minor tick marks will be a subdivision of that, and you can look at it and see, right? If there are 10 of them, it's just 1/10 of the major. Or if you only have 5 of them, then it's 2/10 of the major. Then do you have your axis labeled with units of measure? Okay. Do you have a best fit curve? Now you can best fit a best fit line or a best straight line or a best fit curve, right? Best fit curves are a little more difficult. If you're good freehand, you can draw one in, or if you have a French curve, right? You know what a French curve is. They take different shapes, but they kind of look like something like that. So they have different radius of curvature on that curve. So that allows you to move it around to where it better fits the curve. Because some curves curve like that, and some of them curve real gently. So you can use your French curve to follow that. Let's see, what else am I looking for? I said title, axis, labeled marks, labeled axis, and then draw your points in and your best fit curve. That should do it. Then the rest of this problem is gathering information from your graph. At what volume would the helium sample have a temperature of 5 degrees? So you look at your graph, right? Know how to read a graph. So once you get the curve, the graph made and the curve put in, then you can also say, all right, what volume would correspond to a certain mass here? So you can say, all right, here, over here, down here. There it is. Okay, so you can read data from your graph also. Calculate the slope of the line. So in that case, you would look to see, all right, is it a straight line? Do all these points fall on a straight line? If they do, then you can use any 2 points to determine by difference your delta y and your delta x and calculate the slope. But remember the units of measure. If we do a slope for this line, what would the units of measure be? Well, the change in y is grams. And the change in x is milliliters. So the slope would have units of grams per milliliter. Okay. This one will be a little different because it's temperature versus volume, but you get the idea. And then calculate the y-intercept. So the best way to do that is, like I said before, once you know the slope, you plug in the slope value, and then you pick out an x and a y from your graph. Plug in those numbers, calculate the slope. And when I grade these, I look at your answers and say, okay, is that within so many percent of what I'm expecting? Because there could be slight error here and there, depending on which 2 points you read. So if yours isn't exactly what mine is, doesn't mean it's wrong. Okay, so the next one is pressure volume. All right, this is the one that gives you that, that kind of slope. And you do some of the same things with this one, draw that graph. And then it asks you to do, let's see, 9 parentheses 4. Use the techniques described in this experiment to express the data in a different way. one that will give you a linear graph. Look over here to, here it is, on page 19. That's what they're getting at, right? This is the one that you drew first. And if you transform the volume into its reciprocal and plot that, then you should get a straight line. Okay, so that's what they're asking for in number 9, parentheses 4. So you just need to whip out your calculator and take the inverse of all these volumes and then plot it again on a separate one. And then use the graph that you plotted, the straight line graph, to determine the pressure of the sample when its volume is 40 liters. Okay, here's the trick. If you use the straight line graph, you're not going to find 40 liters on your graph because you took the inverse, right? So if you go to the graph, what are you looking for? You're looking for 1 divided by 40. Then you can go to your straight line graph and say, on that reciprocal volume axis, look for whatever 1 divided by 40 is, right? Is it 0.025, is it? Right, 1/4 is 0.25 and 1/40 would be 0.025. So you go to 0.025 over here to your line and then down, and there you go. Then you find your pressure. Okay? And that's all the required section. We can look at the bonus if you want to. You want to see about maybe doing the bonus? 10 is a bonus. And what we have there is pH plotted against added sodium hydroxide solution in milliliters. So the pH is just a number. You don't even have to put units. You just say pH, that's it. Okay. So it doesn't have in parentheses a unit. pH is just pH. And then the volume of sodium hydroxide is in milliliters. And which one is the independent variable? Excuse me. Which one did you change? You're adding sodium hydroxide to the solution and measuring the pH, right? So the pH is the dependent variable, y-axis. And the x-axis is the added sodium hydroxide. Okay, and there's all your data. It's in 4 columns, but there are 2 groups. Right? They had to do that to spread it so it wouldn't take up the whole page. So you go down 0 through 25, and then over here 26 through 32, and there's your pH for each one. So you notice that the pH is in units of ones, tens, hundreds. So you look at your graph, and probably, here's another thing. If you've got lots of decimal points in one of your on one of your axes, you may want to use the longer axes to get all those decimal points in there. It's easier to read if you can stretch them out. Okay, and that's page 19. And there's an example. Right? It shows you an example. No, excuse me, not 19. 22. 22. Your curve should look sigmoid. When you draw a best fit curve, it ought to be pretty flat along here, and then all of a sudden, shoot, go up like that, and then flatten out again. And let's see, that's parentheses 2 is the graph. And then you say, explain the significance of the large change in pH between the addition of 26 and 28 milliliters. Okay. That we haven't talked about that because we haven't done any titrations. We haven't discussed that. So if you answer that one, you're going to have to look it up. That would take too long to describe here. Let's see, this one, number 11, that's going to be a broken curve, and that's going to be kind of difficult to do. But you do have an example there. Next page. You do have that example to go by. The one trick I would mention is when you're trying to find out what's the change in temperature. I think this is a phase change, isn't it? I think it's a phase change graph. In order to find the difference between temperatures, you want the measurement to be vertical because that's the temperature scale, right? So what's the difference between this section and that section? You can't use any of these numbers because they don't go over here far enough to be vertical, to give you a vertical temperature. So you have to extrapolate that line out here to where you can get a vertical line between the two on the bottom. So you draw a straight line through these and a straight line through that one, and then you find your vertical between the two. That's the trick to doing that. I have some students that don't even draw the graphs in these bonus. They just go in and see how many of these questions can I answer without drawing the graph. But for my key, I drew the graph on my, I think it was Excel. And I used to teach this particular lab as an exercise in Excel graphing. But I found that most of my students didn't have enough background and knew what the graphing was all about to effectively use Excel. So you can do all this stuff in Excel, but you need to understand first how it works. And then the program makes you more efficient. And when you write your formal reports, it's okay. The whole thing needs to be typed, but if you're going to put a graph in it and you're not proficient with graphing programs, Excel or any bunch of others, producing a graph in your computer, then it's okay if you draw it by hand and then maybe take a picture of it and take that GIF or JPEG file and insert it into your report. That's perfectly all right under the circumstances. If you're going to publish in a referee journal, they wouldn't let you get away with that. You'd have to use a graphing program to do it. But in this class, you can do it by hand and then insert it. Okay, any questions?